for joining us for this webinar. We have Mr. Gan here from Bekaert, who's going to be talking to us this evening on FRC and Precast segment tunnel lining. First of all, I would like to introduce our IOM3 Hong Kong branch president, Tim Leung, who has a few words to say. Tim?
Hey, thanks, Jennifer. I won't keep you long because tonight, luckily, we have Gang here to give us a presentation. And this is our first webinar organized by our Hong Kong branch tonight. As per our aims, we promised in the beginning of these terms, we would definitely want to organize more webinars. As you know, because of this COVID-19, we need more CPD for our members and friends. And one thing we want to let you guys know, we Hong Kong branch have our new accounts in the social media, Facebook, LinkedIn, Instagram, and Twitter. Please like and join our social media, and you will see our coming up events in this social media. Now I pass back to Jennifer to start the webinar today.
Yeah. Thank you, Tim. So to introduce Mr. Gan, graduated from the University of Singapore, and he's been working in the construction industry now for 31 years. He's working for Bekaert Singapore as a technical manager since '98, and he's been involved in many of their prestigious underground projects and construction projects around Asia, including the Qingling Railway and Highway Tunnel in Xi'an in China, the Mandai Underground Cavern in Singapore, BMW Shenyang, China, the Daimler Chrysler building in Beijing in China, and the Busan International Exhibition and Convention Center in South Korea, and the Jurong Rock Cavern in Singapore. He's been involved in a number of projects, over 20 featuring fiber reinforced sprayed concrete linings, and over 15 projects featuring fiber reinforced concrete precast segmental tunnel linings. And since January of last year, he's one of the members of the working group drafting the Singapore standard on design of fiber concrete structures. And in March last year, he was appointed as the domain expert for sprayed concrete, and in January of this year was appointed as the domain expert for fiber reinforced concrete under the Intelligent National Productivity and Quality Specifications of Singapore. So we are very honored to have Mr. Gan join us for this webinar, and I will hand the floor over to him now, and I hope you will enjoy. Just before I do hand over, as a note to everyone who's interested in the CPD, there will be a link, so the QR code, a link at the end of the talk. So please make sure to stay to the end, and after that, we will show up on the screen a link so that you can then register for the CPD. Okay, thank you, Mr. Gan.
Thank you, Jennifer, for the introduction, and thank you, Tim and YC, for arranging this talk, and thank you to IOM3. My name is Gan, and my contacts you can see on the slide here. You can either contact me at my email, or you can look for me in LinkedIn. The talk tonight will be about the use of fiber reinforced concrete in precast segmental tunnel linings in Asia. So this is fibers. There are two types of fibers used in Asia. One is steel fibers that is long, and one is steel fibers that is short. This is short steel fibers, and this is long steel fibers. And you also have macropolypropylene or macropolymer fibers, or the micropolymer fibers. And for precast segmental linings, these two fibers are used in combination. The long steel fibers below and the micropolymers. They are mixed in concrete together and used to cast the precast segmental linings. So our topics tonight will be in 4 sections. Application of FRC, fiber reinforced concrete, QA/QC of fiber reinforced concrete, design of fiber reinforced concrete, and durability of fiber reinforced concrete. For application of fiber reinforced concrete in Asia, until this year, we have, you can see that we have completed about 51 kilometers of fiber reinforced concrete precast segment projects. Here you will see 15 projects. The highlighted yellow projects are still ongoing. The others have completed. Most of the jobs currently are located in Singapore because acceptance level of fiber reinforced concrete in Asia, Singapore is the highest acceptance level, followed by Malaysia, and then Hong Kong, and as well as Japan. So over 51 kilometers of tunnel linings have been reinforced with fiber concrete. This is one of the projects in 2014. This is the Thomson East Coast Line contract T206, which is built by Shanghai Tunnel Engineering. And this is the segment that is casted, and these are the segments for the project in Thomson Line T206. And actually, you can't really see any fibers that pops out on the surface. This is for Thomson East Coast Line T207, built by Shimizu Corporation, also in Singapore. And this is a close-up of the segment for T207. And on the photo, on the picture on the left-hand side here, you can see some rust stains on the surface. So these rust stains are caused by the fibers on the surface that have rusted. So these are the worst case scenario that you will see. And it doesn't mean that the segment cannot be used, because it is all purely aesthetic. This is use of fibers in the Lien Tang Road Tunnel project in 2017 in Hong Kong, built by Dragages and precasted in Redland Precast in Dongguan. And these are the thickest segment so far that is using fiber concrete combined with rebars. This is hybrid segment. The thickness of the segment is 500 millimeter, but purely this is because of the diameter of the tunnel, which is 12.6 meter in diameter. And here you can see the rebar cage. It's a light rebar cage combined with steel fiber concrete. Yeah. So this is for Liantang project. And here in a damaged area here, you can finally see the fibers that is rusted. Otherwise, it's quite difficult to find the fibers. So here, I just wanted to show you where the fibers are. So the fibers are mixed everywhere inside the concrete. It's homogeneously distributed. Yeah. So they are inside the concrete. And to really see it is quite difficult unless you really damage that corner. Yeah. This is a recent project in 2018. This is the Circle Line Phase 6 Contract 882 in Singapore. Again, on the right-hand side, you can see the close-up of the segment. We can't see the fibers at all on the surface. This is built by China State Nishimatsu Joint Venture. And this is how, on the right-hand side, you see the bucket pouring fiber concrete into the mold. And on the left, these are the mold. And these are the completed segments, 7+1. So 8 segments are stacked together, and there is no problem with the loads. And over here, you see a big swimming pool. This is the curing pool for the segments. So segments are cured inside a swimming pool. It's water cured. This is Circle Line Phase 6 Contract 885, also in 2018. This one is built by China Rail Tunneling Group. And again, here on the right-hand side, you can see the close-up of the segment. Again, no fibers on the surface. And here you see the segments that is just finished. And in the middle here, you see the wet fiber concrete that is not yet finished. It's still on its way to be finished. On the right-hand side, this is already finished. And on the left, it's the pouring of the fibers into the mold. And then you have the Northeast Line extension, contract C715 in Singapore again. This is built by China State. And again, they do the curing in a swimming pool. This is unfinished fiber concrete. And over here on the right-hand side, this is the finished fiber concrete. And in the bottom here, you see fibers being poured into the mold. And these are the completed segments. Again, stacking is 7+1. So it's 8 pieces stacked together. And in Japan, you have the Kasaibashi TEPCO cable tunnel. This is in 2018. And it's built by Ando Hazama. But this is a small diameter tunnel. It's only 3.5 meter. It's for cables. Yeah. And this is the thinnest segment that we have been involved so far. And on the right-hand side, you will see a segment that is damaged. See this segment that is completely damaged after testing. So this is a segment with steel cage. There is no fibers in there. So this steel cage segment is completely damaged. Yeah. After testing, and it contains rebars. Yeah. And then here, you will see the segment that is rebar combined with steel fibers. And you will find that there is no spalling at all. It's many cracks. What this means is that it's a redistribution of cracks. The cracks are redistributed in fine crack widths. So the cracks are everywhere, and this is good. Why? Because it means that this concrete is working well. Yeah. So these fine cracks actually is it doesn't cause any structural problems because this testing is tested to failure. The segments are tested to failure, and this is at failure mode. Yeah. So at failure mode, all you have is fine cracks. And then in 2019, last year, we started on this project called the DTSS, deep tunnel sewer system phase 2, contract T07 with Zublin. And this is the precasted segment on the right. And you can see that you can't find fibers on the surface at all. This is pictures of the segment. It's 6 segments stacked together. Yeah. So the diameter of the tunnel is between 3.5 to 6 meters. So some of the segments are kind of small. Yeah. And over at the bottom here, you will see a dosing equipment. These are automatic dosing equipment to dose steel fibers into the concrete batching plant. So this dosing equipment, the special thing about it is that it's set up to plus or minus 1% dosing accuracy. This is the requirement for Singapore projects. The dosing accuracy is plus or minus 1%. So it's a very high dosing accuracy, and as a result, you need to set up the dosing equipment in a good way. Otherwise, we can't achieve the plus minus 1% dosing accuracy. So what is the future? What you saw just now was all the projects that have been going on. The future is this. The first one is Singapore Cross Island Line. This is the first time that such a project in Singapore has 11 contracts with fiber reinforced concrete precast segmental lining. In this project, it's a project with 13 contracts, but out of 13, 11 of them is with fiber reinforced concrete. And underneath Singapore Changi Terminal 5, the new Terminal 5, you will have the inter-terminal bored tunnels. And this is again fiber reinforced concrete precast segmental linings. And for the postponed high-speed rail, it is also specified with fiber reinforced concrete precast segmental lining. And finally, again for the postponed Malaysia Klang Valley MRT Line 3, the 30 kilometers of tunnel, the longest in Asia, is proposed with fiber reinforced concrete precast lining as well. So this is the future. What this means is that fiber concrete has already received acceptance from authorities in Singapore and Malaysia, and mainly because of one thing, durability. Because of higher durability than traditional segments, they get more confident and they decide to use more fiber reinforced concrete for the precast segmental linings. Then we come to QA/QC of fiber reinforced concrete. Fiber reinforced concrete specification in Singapore. This table that you see is coming from a paper written by 2 gentlemen from LTA. One is Dr. Goh Kok Han and one is Dr. Wen Ta Zi. Dr. Wen is now with Changi Airport Group for Terminal 5 tunnel project. And their title of the paper is Design Practice on Tunnels and Tunneling in Singapore, Current State and Future Trends. So this table came from the archives of LTA. It's basically telling you what is the specification requirements of fiber concrete in Singapore. Characteristic tensile strength is around 4.5. Characteristic LOP is between 4.2 to 7. Characteristic FR1 is 2.8, and today it is 5.2. Characteristic FR4 is 1.4 in the first project, and today is 2 MPa. So the requirements for fiber concrete is getting higher and higher. Why this is so is because at the beginning, fiber concrete was designed as plain concrete. So they didn't take into account the contribution of fibers. But in later projects, they try to take into account some contribution of fibers. As a result, you need higher FR1 and higher FR4 numbers. And FR1 is connected to serviceability limit state designs, which means durability designs is connected to FR1, and FR4 is connected with ultimate limit state design. So when you talk about bending moments and you want to have higher bending moments, you need a higher FR4. And these are other fiber reinforced concrete specifications in Singapore and in Malaysia. And for Malaysia, the last two projects, line 1 and line 2, you will see that characteristic tensile splitting strength is 4.8, LOP is 5, and FR1 is around 5, and FR4 is 3.4. So FR4 is highest in Malaysia. And it's mainly because they are considering the contribution of fiber concrete for the bending moments. So with a higher FR4, they can design for higher bending moments. And this is Thompson East Coast Line, T316. This is ongoing. This is currently being precasted. And they are using 4.5 for tensile splitting strength. LOP is a very high 7. FR1 is 5.2, and FR4 is 2. And lastly, you will see the Changi interterminal board tunnels. Tensile splitting strength is 5. LOP is 5. And FR1 is 4.8, but characteristic FR4 is 2.3. So it's slightly higher than the LTA's requirement. So they probably need a higher bending moment as well. And then QA/QC of FRC, one of the things that we always do every day in the precast plant or on site is we check for the fiber dosage check in the concrete. So there is a standard for this check, and the standard is BSEN 14721, and I just show you a very quick video. So what happens is that you are pouring wet fiber concrete into this machine, and then what comes out of it is the aggregates, sand and cement. Yeah, but where are the fibers? The fibers are here on the right hand side. They are stuck to the magnet inside this machine. With this magnet, you can then collect your fibers, you weigh it, and immediately within 10 or 15 minutes, you can already do your fiber dosage check. So this speeds up the checking of the fiber dosage very fast, and as a result, we do this type of check every day. Yeah. Because it's important to make sure that all the fiber amount that is inside the concrete is consistently the same at all times. The next QA and QC that is tested is BSEN 14651. It's a beam test. And this one is also done almost every day. Now, this is a beam that is recently tested on the 24th of July this year. This is for the Thompson East Coast Line T316 project. So this beam is completed already. And what you see below here, this is a CMOD transducer. It's called a crack mouth opening displacement transducer. So they measure the crack mouth that you see at the bottom of the beam here. And then this is the testing setup for the beam test. And the test setup actually has certain requirements, which I will tell you afterwards. This is the result from the test, and you will see a test curve like that. And then over here, this point here, this is the LOP. This is the point whereby the first crack of the fiber concrete occurs. And you can see that the point where the first crack occurs is actually around 0.05 millimeter crack mouth. So it's very, very small. So you need to capture this point. Otherwise, if you don't capture this point, then the points behind at 0.5, at 1.5, at 2.5, and at 3.5 will be wrongly obtained. And when it's wrongly obtained, then you will get wrong results. That means this curve could be way below, and it's not at this level. Yeah. Okay. So this is the requirements of the testing machine. Again, I took this from a magazine called Concrete Technology, and this paper appeared in this magazine, and it says like this: the rigidity of the loading frame in 2 to 3 meganewton per millimeter deformation range is the main crucial factor in attaining unadulterated results. So you must make sure that your test frame over here has a rigidity of 2 to 3 meganewton per millimeter. Then this rigidity is essential to be able to record the first crack of the deformation and ultimately to describe the construction components resistance. Yeah. So we need this to capture the first crack. Otherwise, the back end of the results will also be wrong. So due to these special requirements, the loading frame and its column, braced and free of play, possess a total weight of 3.8 tons. The entire testing system weighs almost 6 tons. So you need to, again, we need to make sure that the total weight of the testing setup is about 3.8 tons to 6 tons. Yeah. Then this is a short video of a beam test. Okay. They are adjusting the beams so that it sits . They are installing the frame, the testing frame. They are installing the CMOD transducer. Then they are starting to test. The results can be seen immediately. Yep. And then the cracks have happened. And this is the curve. Okay. And these are the results. Yeah. The results are presented in this manner. So for one truck, for one mix design, you need to do 3 batches. One batch, you have to do 20 beams. Yeah. So B1 to B20. So for one mix design, you do 3 batches, means you test 60 beams. Why we test so many beams? It's because of these 2 things: standard deviation and coefficient of variance. When we test more, then the standard deviation and coefficient of variance become more confident. And you have a smaller coefficient of variance. And this is important because consulting engineers are going to use these results to input into their bending moment calculations, which means they are going to input FR4. Yeah. So FR4 is going to be inputted. Now, we look at this batch 1, the minimum and maximum. FR4 minimum is 6.8, maximum is 12.5. So coefficient of variance is 19%, is rather high. Now, let's go to another batch. This is batch 2. Minimum is 5.4, maximum is 10.8. Coefficient of variance is 17%. Batch 3, this is concrete mix 2. The second, what we call the spare mix, just in case the first mix doesn't, the materials is not available, you have a spare mix so that you can continue casting in case the mix 1 material is not available. And again, this is batch 1. You will see coefficient of variance is 20%, minimum is 5.6, maximum is 11.2. But here, in batch 2, you find that minimum is 3.4 and maximum is 13. The coefficient of variance is almost 30%. So what happens if we only test 3 beams and one of our beams is 3.4, while we have to make sure that we get 1.7, yeah? So the correct result is 1.7. We need to get 1.7. This is the required characteristic value, 1.7. And then the compliance is that 1.7 must be above by 1.4, meaning 1.7 plus 1.4 is 3.1. So the compliance is 3.1. Right now we are getting 3.4 for the lowest value. So in case we only have 3 beams, or in case we only have 6 beams, and one of our beams is so low, we will never be able to hit the characteristic value here. That's why we need to test at least 12 beams, not 6, not 3, not 9, but at least 12 beams. In Singapore's case, they are testing 20 beams. This will give more confidence to engineers who is using these numbers to do bending moment designs. Yeah. So why is FRC flexural beam testing so important? Yeah. So it's because we are going to use these numbers in our design. That's why they test so many. And here, design of FRC. So now we are going to design of fiber reinforced concrete, and I want to show you one example from the UK Concrete Society Technical Report 63, published in the year 2007. Yeah. So here, these 2 pages, you might not be able to see it clearly, but I have taken it out and I have blown it up. So compression equals to tension. Yeah. So you see the stress blocks here, and then compression equate to tension, and then you get this number, you get this formula, and from here you find that it involves sigma 2, and it involves FB. FB involves sigma 2 and sigma 3. Now, what is sigma 2 and sigma 3? Sigma 2 is FR1 and sigma 3 is FR4. So these are characteristic value. And apart from being characteristic value, which is already very safe, the Concrete Society put in a reduction factor of 0.45 here for FR1 and 0.37 for FR4. Why do they do that? Because FR4 always have bigger coefficient of variance. So the bigger the coefficient of variance, they want to put more safety. So it's 0.37. So they only allow you to use 0.37 of the FR4. And apart from that, they put in another factor K here. And this factor K is less than 1. So you are reducing your FR1 and FR4 further. Yeah. So that's why it's so important to be correct and accurate and consistent for the FR1 and FR4 values. So these FR1 and FR4 are the characteristic residual strength values at 0.5 and 3.5 millimeter derived in the BSEN 14651 beam test. And after that, you calculate your moment of resistance, and you find that in this calculation, you need the term FB and you need the term sigma 2 as well. So FB is a function of sigma 2 and sigma 3, and sigma 2 is a function of sigma 2, and both are functions of FR1 and FR4. And that is why we need to test as many beams as possible so that we are confident with the FR1 and FR4 results. Because today, using fiber concrete is no longer a strange thing, but the strange thing is to ensure that we can make the consistent quality of fiber reinforced concrete. For design, there are so many guidance document and codes today. The first guidance document appeared in the year 2000 from Rylam. It's called TC162. Subsequently, came out in 2007. Just now, what you saw was Concrete Society Technical Report 63. And then in 2010, you have the FIB Model Code. And from then on, all the other guidance document or standards you see below FIB Model Code is all based on FIB Model Code. Everything here, Swedish Standard, ACI 544, ITATEC Guidance, British Standards Institute, PAS 8810, FIB Bulletin 83, ITA Report number 22, and the very new Singapore Standard Design of Fiber Concrete Structures, which will be published in October 2020. All these are based on FIB Model Code 2010. All bending moment calculations are using FR1 and FR3 or FR4 in the calculations. And these values come from Flexural Beam Test, BSEN 14651. If this test produce inconsistent results, structural engineers cannot produce structurally sound designs. Yeah. Then we are coming to the final stretch of our talk, and this is about durability of fiber reinforced concrete. Many people always ask, how durable is fiber reinforced concrete? The first thing we should talk about is crack resistance. This information is extracted from a paper called Shrinkage Cracking of Fiber Reinforced Concrete, published in ACI in March 1990. It's so long ago. Okay, look at figure 11. Let's say you are using 0.5% of fiber. 0.5% of fiber is 40 kilograms of steel fiber. So if you bring this line up to this curve, you will find that the average crack width is 0.1 millimeter. So when you use 0.5% of fiber by volume, which is 40 kilograms per cubic meter of concrete, you can achieve already 0.1 millimeter crack width. This is confirmed in March 1990, not now. And then this curve, figure 12, this is for polymer fibers. If you use 1% fiber volume, 1% is a 9.1 kilogram of polypropylene fibers or polymer fiber, and bring the curve up, you will find that it also achieves crack width of 0.1 millimeter. So both types of fiber can achieve 0.1 millimeter crack width. It's no problem at all. In fact, we don't even need 0.1 millimeter. We are actually specifying 0.2 or 0.3 millimeter, but you can actually achieve as small as 0.1 millimeter. So all types of fibers can provide 0.1 millimeter crack width. It's all about dosages. Yeah, so we need to test the different dosages. And this is proven in 1990. Then we have another paper written by Professor Tan from National University of Singapore. And this is a 10-year study on fiber reinforced concrete beams under sustained loadings. So they made the beams in 1994. And then they tested a portion of the beams in 1994. And then after that, what they did was they load up the balance of the beams in this configuration. So the load is sustained. And they waited until 2004. So they waited for 10 years. Yeah. And then they wanted to see what's the difference between 1994 and 2004. This is how long this study went. Yeah. This was published finally in May 2005 in ACI. And here you will see some results. First of all, they were looking at deflection of the beams after 10 years. Now, you will see the curve might be small, but for those who want more details, I have all the papers, so I can send all the papers to you. A means plain concrete. B, C, D, E means fiber reinforced concrete with different dosages. So E is the higher dosage and B is the lowest dosage. So from this curve, you will see that fiber concrete shows lower deflection than the plain concrete after 10 years. Yeah. So let's go to it. Another one. FRC crack width after 10 years. So this is crack width. And A again is plain concrete. And B, C, D, E is fiber concrete. B is 0.5% of fiber. So B is 40 kilograms of fiber concrete. C, D, E is higher dosages of fiber concrete. So you can see that in year one, 1994, the crack width for the fiber concrete is about 0.1 actually. And after 10 years of sustained loadings, it's still around 0.1. So it didn't increase. The amount of crack is still at 0.1. But if you look at the plain concrete, the crack width goes beyond 0.1. It's closer to 0.2 after 10 years. And last of all is flexural beam test results. So they were comparing the flexural behavior of the beam in 1994 and the flexural behavior of the beam after 10 years. So here, 22.27, these are in year 0. Here, 22.58 is after 10 years. So in fact, after 10 years, it doesn't change at all. It doesn't reduce and it doesn't increase. It's still roughly the same. That's why PA over PO is equal to almost 1. Yeah. So these are the summary of their findings. The main conclusion, the addition of steel fibers to concrete is effective in containing long-term deflection and restraining crack widening. The effect is more obvious with time. Steel fibers can therefore be seen to serve as tensile reinforcement. So 40 kilograms of steel fibers can provide 0.1 millimeter average crack width. This is proven in 1990, confirmed again in 2004. More on durability. Here we take an extract from ITA report number 16, published in April 2016. And this is a report that talks about 73 fiber reinforced concrete precast tunnel segment projects around the world. So one of the special conclusion is found in page 63. And this is for the Doha Metro in the Middle East. With regards to the corrosion, it is assumed that for concrete reinforced with fibers, this may occur due to carbonation of the intradoor surface, which is limited to the near surface area of the segments. This localized corrosion of the steel fibers do not cause damage, cracking and/or spalling of concrete, and it is consequently not considered problematic for the entire required service life of 120 years. On the basis of the above, no specific durability design is necessary with regards to corrosion of fibers. Yeah. So this is confirmed by ITA Report 16, published in 2016. And this is just a extract from the same document. And then this is published by British Standards Association. It's called PAS 8810. The title is Design of Concrete Segmental Tunnel Linings, Code of Practice, published also in April 2016. And here, if we look at page 25, yeah, for steel fiber reinforced concrete, minimum concrete cover recommendations only apply to the embedded bar reinforcement, not to the steel fiber. So we do not provide concrete cover for steel fibers. Steel fibers can corrode when passivity is lost due to carbonation of the surrounding concrete or due to ingress of chloride in a similar way to normal reinforcement. As described in 7.922, predictive models can be used to determine the required properties of concrete or the need for additional methods of protection to restrict the extent of corrosion of fibers such that it does not adversely affect the performance of the lining. Corrosion of carbon steel fibers close to the surface can cause rusting. So again, it's confirming that it is an aesthetic issue. It is not a structural problem. This again is extracted. This page is extracted from the same document. Then we have a paper written by Cowie. Cowie is a consultant involved in a lot of tunneling projects as well, published in 2018. They talk about their tunneling projects in the Middle East. And in page 11, they discuss the Idris sewage tunnel in Doha. And for the Idris sewage tunnel, it requires the transport of sewage with the risk of microbiological attack of the concrete. Hence, the employer requires a double protective design to mitigate such attack of the segmental lining. A sacrificial concrete layer not to be considered as part of the permanent structure, and an internal HDPE membrane. The sacrificial concrete layer and the structural part of the segments were cast using the same concrete mix design. And that concrete mix design is a steel fiber reinforced concrete mix design with high content of supplementary cementitious material, GGBS, and a low water cement ratio, less than 0.4. So this is the same solution used for the deep tunnel sewage system, phase 2 in Singapore now. It's under construction now. Again, this is a blow up of the extract that I just mentioned. And you have another report published in 2001 by a concrete group in Europe. It's called the Bright Europe Group. And here they mention almost the same thing as the British Standard Institute, mainly surface corrosion, and the corrosion does not penetrate into the concrete. Yeah. And the final conclusion made from this durability study of FRC is this: carbonation depth in all samples is very small, 1 to 2 millimeter, even for specimens dried out in CO2 environment. Type of concrete seems to be the determining factor. Now, your precast segment is normally 200 millimeter to 500 millimeter thick. Now, carbonation is only 1 to 2 millimeter. So this is a non-structural problem. It is an aesthetic problem. Yeah. So we can even say that we we increased the thickness of the segment to 202 millimeter just to take care of the carbonation. Yeah. Rusty fibers could be found in the non-cracked concrete only directly at the surface in the carbonated zone. Galvanized fibers at the surface do not show staining. Again, fibers only stain on the surface. It's non-structural, it's an aesthetic problem. Zinc-coated fibers show a positive effect towards corrosion resistance. No staining at the surface and no corrosion of the steel could be seen, although the zinc layer at some places has disappeared. The crack width up to 0.5 millimeter seems to have no adverse effect on corrosion. Now, for rebar concrete, we cannot allow 0.5 millimeter. But for fiber concrete, we can actually allow until 0.5 millimeter and it still have no problems with corrosion. So this is the conclusion that is already published in 2001. And a last paper that came out in 1990 by some Japanese researcher, Dr. Kobayashi. Sadly, Dr. Kobayashi has passed away, but this paper is the only paper available whereby it went through a long-term study. They casted a bunch of concrete girders reinforced with rebars and steel fibers. And it was a 5-year-long study. In the end, he found that the concrete girders without steel fibers, the rebars were completely corroded, while the concrete girders with steel fibers, the rebars was protected from corrosion by the steel fibers. This is amazing information, but it already been published in 1990, just that nobody knows about it. And again, it was mentioned that steel fibers corrosion was limited to superficial surface corrosion and nothing more. Yeah. So, and this test was done in a marine environment. So it's very stringent, very high salt, high chloride marine environment. Yeah. So this is the extract of the conclusion from that paper. And again, if you need the full paper, you can just ask for it and I will definitely send it to you. So based on the assessment 1 to 6 just now, we basically need not do anything with regards to the rust stains on the intradoors. It is purely an aesthetic problem and will not cause structural damage. Last words on durability of FRC, fiber reinforced concrete. I just wanted to show you an old project that was completed back in 2013. Look on your left-hand side, this white portion here, it's a very long building. Okay, this building is 1.1 kilometer long. This is the longest X-ray free electron laser slab in Asia. It's 1.1 kilometer long. The width at the end here is 20 meters. And when it comes to the end of 1.1 kilometer, it's about 6 meters. So the slab width is 20 meters to 6 meters. So it's a very narrow slab and very, very long. And the slab thickness is 500 millimeter. And it has no contraction joints. They only use construction joints, but no contraction joint. No contraction joint means no saw cuts. So this is the longest steel fiber jointless slab in Asia. And believe it or not, in 2019, the owner of this facility, which is the Korean government, confirmed to the contractor that after 2013 to 2019, after 6 years of usage, the slabs still have no cracks. This is a confirmation that fiber concrete can work to prevent cracks. Yeah. And this is how it was casted. It was casted with a bucket and they just pour directly onto the narrow slab, and it was done without any saw cuts at all. And last words on durability. Durability is a favorite topic of mine, and this last slide that you see has nothing to do with fibers at all. This is a bacteria powder. It's a dry powder that is a bacteria. Now, the The product name is called Bacillus Healing Agent. And what is amazing about this product is this. Let's say you have a structure, a tunnel lining that is cracked up, and none of the cracks are more than 0.8 millimeter. So what do? You take 10 kilograms of this bacteria powder, mix it into water, and you spray it at the cracks. After several days, these cracks will start to heal by itself. It basically disappears, the cracks. What has happened? What has happened is the bacteria is activated after you add water. And when the bacteria is activated, it starts to eat something. When it starts to eat, it will start to, pass motion. And the pass motion is the product that seals up the cracks. So it will heal the cracks. So this is what they call self-healing concrete. And this is the best product that I have ever seen being introduced in this last 2 or 3 years. It's not heavily used yet, but it's an amazing product. Imagine, as I have already told you, fiber concrete can control the cracks to 0.1 millimeter. Now, if you add this bacteria powder into fiber concrete, I think you can finally say, I have made crack-free concrete. Yeah. So this is an amazing product. It's not from us. You can get more information from www.basilisconcrete.com, or you can just type in Google self-healing bacteria concrete. It's a wonderful product, and I think when you use together with fiber concrete, you will get amazing results. Last words. As usual, I learned from my mentor, and at the end, he always tell the audience, your hole is my goal, and tunneling is an art. Thank you very much. And if you have questions, you can ask, or you can also send me an email. Thank you.
Thank you very much, Mr. Gan. If there are any questions, please raise them in the comments section and we can then unmute you.
Maybe I ask the first questions. Again, early age of steel fiber application in Malaysia. Involved in KVMR2. At that moment, we found difficulty on having high FR4 value. In one of your slides, it's up to 4.8 megapascal FR4.
Hold on, let me go back to that slide. FR4 for KVMRT is 3.4.
At that moment, I don't know whether you know or not, you got that moment with a competitor, which is now merged it. At that moment, nobody can have that high value as a guarantee. So eventually we found a problem having high strength concrete. We do not have sufficient strength for the tensile strength of steel. We will do that. So can you recommend us the best value as a combination for nowadays or future high strength segments that we need? So what are we targeting, or at least to get the tensile strength of steel? To high value.
I understand. Back in first of all, let's have a look at this. Okay, so let's have a look at this results. We take beam 7, B27. you will find that the concrete compressive strength is 92 megapascal. Yeah, it's very high. Now, what was the required compressive strength? The requirement is 60.
Sorry, Mr. Gan, the screen has gone green.
The screen has gone green.
The presentation screen. I think there's somebody else that isn't able to see it either.
Okay, hold on. I didn't change the screen. Wait.
Okay.
Right.
Is it better?
Yeah, yes, perfect.
Okay. So if we look at B27, you will find that the concrete compressive strength is 92. This strength is too high. Look at what is required is 60, but it's at 92 over here. So what happens is that you will still achieve your LOP, which is 7.8, and you will still achieve your FR1, which is 8.6. But as you go down the line to FR4, when it hits FR4, the fiber will start breaking. And because the fibers start breaking, you will start seeing lower values of FR4. So how to solve this? How to solve this is you need to use higher strength fibers. In back when we were doing, let me show you the curve. Okay, so if the concrete compressive strength is too high, this back end will drop too low. Yeah, and this is, when it drops, it's purely because the fiber itself is breaking up. So fiber breaking, what does it mean? That means these fibers here, the hooks here are actually breaking. So when the hooks are breaking, it will release the strength. So that's not good. So what happens is that you need a higher strength for the steel fibers. Back in the first KV MRT Line 1 project, at the very beginning, they were testing fibers with a tensile strength of 1,200 megapascal. And with that, it was impossible to achieve the high FR4 requirements because the fiber keep on breaking at the end. So later, what we did was we introduced a fiber with a tensile strength of 1,550. And with that, we could solve the fiber breaking problem. It's not solved, but we reduce the breaking of the fiber. So less fiber are breaking. So as a result, it can achieve the FR4 values. I hope I have answered your question, YC.
We got a question from
the floor, suppose.
From the audience. So can you read out, Jennifer?
Yes, there's a question here from Kiwin Ku, I hope I pronounced your name correctly, on have you worked on a non-linear model to predict cracks in structures?
Non-linear model, no. No, I have not worked on a non-linear model.
Okay.
Yeah.
The next question is from Werner Grégoire. Do you check the orientation and distribution of fibers in the mold?
At the moment, we do not have the technology to check the orientation of the fibers, but in about maybe 2 months' time, I will receive this technology from Barcelona, and by December, I should be able to tell you the orientation of the fibers in any concrete mix, actually, because the technology is already created by a group of very smart people in Spain. And we have purchased one of their equipment to check this orientation of steel fibers inside concrete. So in about 2 months' time, I will receive this equipment. So maybe in December, we can do a webinar session like that, and I can show it to you on screen, orientation of any fiber concrete. Yeah, it's possible.
I think that would be very interesting for our members.
Yeah.
To follow up on that, will you then use that to do research on the impact of orientation on strength?
Yes, because it will give us a lot of additional information. And what we plan to do is we plan to provide this type of equipment to the different fiber concrete projects that is using fiber concrete for making precast segments. So we are thinking of lending them this type of equipment, and then from there they will share with us the results, and then we could collect all these results from different projects, and we can share it with the whole world. Actually, we can share it with ITA. Yeah, it's a very good way to understand better how well the orientation of fibers affect the performance of fiber concrete.
Look forward to hearing how the research goes. Are there any other questions from the floor?
No. Let me ask the last question, right? Okay. According to your video, I can see you did a 0.0 test on the beam. Have you done the 2.0 test so that you can get a pure bending moment or fracture?
Hold on. Point load test.
Yeah, the video is showing a single point load test, right?
This one, single point load. Yes, this one.
Have you done the 2.0?
Yes, we do a 2-point load if there is no notch below. That means I do not cut the beam. This beam has a cut at the center. Tim, if you look here, it has a cut at the center. So because there is a cut at the center, what I do is I just use 1 point and push it, and it will crack at the exact line. Now, if I don't cut the beam, then I'm going to use a 2-point testing.
All right.
Yeah.
So that you get the flexural strength.
Yeah, so that I will get the flexural. But today, because BSEN 14651 is the recognized test method, all beams have to be cut. So if I'm cutting the beam at the center here, then I will just use a 1-point load, and I use a CMOD to check the deformation. So the other test that you mentioned is 2-point load. 2-point load, I don't check the CMOD. I will use a displacement transducer to check the deflection.
Okay. Thank
you.
Okay, we've had a couple more questions come up.
Yeah.
Maybe we'll ask 2 more questions, and then YC, you can put up the access through to registering for CPD for everyone. So the first question here is, if you keep increasing the strength of the fiber, as you mentioned, having those little hooks that if they become too brittle, that can impact the strength. But if you increase it, does it become more brittle and easier to break, and therefore causes breaking of the concrete sample?
No, it doesn't become more brittle in concrete, because if the strength...
If you made the fibers, if you strengthened them, would you pass a point where they would then become too brittle?
Yeah, not for tensile strength of up to 3,000 MPa. The steel can go up to 3,000 MPa and will not break easily in concrete, nor will it cause the concrete to break. Yeah. Okay. So up to 3000 MPa is still fine. The only problem is production is very difficult. Now, if the steel goes to 3000 MPa, then it's very brittle, and to produce the fibers is extremely difficult because then it's easy to break when we are trying to cut the fibers. So production of the fiber will become very difficult. It's not usage. Usage is still good.
It's interesting. It's more the fabrication as opposed to the usage that's a problem. Okay.
Yeah, it's the fabrication. Yeah.
Yeah. Okay. The next question is do you have any experience or is there much research in comparing the performance of fiber reinforced concrete when not precasted but cast in situ sprayed? Possibly one of the examples is that a 1 kilometer long slab where it was one section through the bucket.
Yeah. For cast in situ or sprayed, basically cast in situ is having the same performance as precast concrete. Yeah. So because cast in situ, you can control the quality of the cast in situ fiber concrete. So performance-wise, it's the same as precast concrete. Now, sprayed concrete is different. Sprayed concrete, because your fibers is going to be rebounded. So because of fiber rebound, your performance when compared with cast in situ or precast concrete will be very, very different. And for spraying, we need skilled nozzle man. That's why if the nozzle man is not happy on the day that he's spraying or he's having an argument with his wife, then you shouldn't let him spray any concrete because all the fibers will be dropping into the floor and it's not inside the concrete anymore. So for sprayed concrete, it's more tricky. But for cast in situ and precast concrete, it's the same.
Okay, thank you very much. Perhaps then, Weiss, if you can upload the link. And I'll take this opportunity to thank you very much, Mr. Yan, for your very informative talk. I've had lots of comments of everyone saying thank you so much for the brilliant presentation. So really, thank you very much for taking the time to speak to us today. And look forward to hearing the update when you have the new equipment, being able to analyze the orientation of the fibers.
I would like to share. I would like to share the information that I get from the new equipment with everyone as well. And if you wish to get in touch with me for more questions, you can find me on LinkedIn and just add me, and I will be able to answer your questions. As well as I have a lot of technical posting in LinkedIn, so you can read my posts there as well. Thank you.
That's very kind. Thank you. And I think some people have asked whether you might be willing to share the presentation.
Yes, the presentation is already with YC, with IOM3. So for those who are interested in it, IOM3 can send it to your emails. Just provide your emails to IOM3 with the QR code, and they will send the presentation to you. And if you can't get it, just look for me in LinkedIn and I will send you the presentation.
Jennifer?
Yes?
Before we end the webinar, I would like to say thank you to once again. And I would like to say thank you to YC for arranging this webinar, and yourself, Jennifer, George, helping us in hosting the fire. And actually, I would like to thank everyone who support us. According to the technical problem, we this time only can have maximum 100 participants. In fact, that our Zoom system can go up to 500. So never mind. Next time. However, this webinar we have recorded. We will cut the nice version and then upload it to our branch website, such that who missed the chance to have this webinar tonight, they can watch our video version. So thanks very much.